Good afternoon. This is CIVE 634, Surface Water Hydrology. This is class number 122, 12 for 12th week of the semester and 2 for the second class of 2 classes that we teach every week. My name is Professor Victor Ponce, and I'm with the Department of Civil Engineering at San Diego State University. The subject today is the actual comparison between the convolution technique of Sherman and the cascade linear reservoirs of Don Newton, the SAR method, 1954, I believe. 1954 it was developed. The manual dates from 1954. So that's what we're going to cover today. Let me get to the syllabus. I already covered G17. That was it this Monday. I talked about theory of the general dimensionless unit hydrograph. There's also a video, by the way, but you can watch the video on your own time if you so need to do that. Today, we're going to be talking about this paper, is cascade and convolution, one and the same. And there's also a video of it. So this is the story, cascade and convolution, one and the same. First, a little bit of history. You know, Professor Ponce loves history. In 1932, Sherman came up with the concept of unit hydrograph, even though in the literature, people like Marcus have argued that he was not the first. That doesn't matter. Was he number 1 or number 2? It doesn't matter. He is credited with having been the developer, quote unquote, of the concept of the unit hydrograph. What does the unit hydrograph do? It creates a hydrograph for a unit impulse of rain. And the unit impulse is not even intensity or duration. It is a unit. It's 1 inch or 1 centimeter or whatever unit we wish to use. So that's what Sherman did, presumably in 1932. I know he published it in 1932. I have read the original Sherman paper. What I have not read is the claim of some people that say that in 1928, there was a couple of guys that wrote about the same subject. That's another story. We don't really care about that at this point. Too many years have passed. 1932, imagine, 90 years ago. Okay, that's the granddaddy of the modeling of diffusion, because we are modeling diffusion. The unit hydrograph is a tool to model diffusion for floods. It was not called that at the time they did it, but they were doing it. They just didn't know that the word diffusion was so prevalent at the time, or I guess not prevalent, but that it was everywhere. Diffusion is everywhere. So then in 1950s, the Army Corps of Engineers was charged, or I guess was in charge of doing the dams on the Columbia. There were a whole lot of dams and they had to do a lot of hydrology. And they charged Don Newton to develop a model, which he called the SAR model, the stream flow synthesis and reservoir regulation. And what he did is he took all the flows and he divided into 3, the flow on the surface, flow in the inner flow, and the flow in the groundwater. And then he had to devise a way of figuring out the diffusion of these 3 components. Remember, the runoff was separated into 3 components. And he knew that they had different diffusion properties, or diffusion characteristics. So he developed the cascade linear reservoirs, which is a way of calculating diffusion or imposing a certain amount of diffusion on the calculation. And if you have, say a current number low, it's a lot of diffusion. A large number of linear reservoirs, a lot of diffusion. Otherwise, if the current number is 2, the diffusion is nil, 0. And the lower the number of reservoirs, the less diffusion, and so on and so forth. Basically, we all know that the cascade linear reservoirs is a way of calculating diffusion, meaning just generating unit hydrographs too, or hydrographs that have already diffusion built into them. So that's the story with these 2 gentlemen, Sherman and Don Newton. I believe it's Don Newton now. The other day we were doubtful about that. Then I have worked with these methods since I would say I taught hydrology for many years. I mean, how many years? More like 30 years. I taught hydrology at San Diego State for 30 years. I knew the theory and the practice of the unit hydrograph back and forth. That's the unit hydrograph. And then we were lucky that in 1979, I was invited to go to Brazil to use the SAR model. Not use it, but work with the SAR model. So I became aware that the SAR model did exist and how it was put together. And when I came back in 1980, I wrote a paper on it, on the SAR model and the features of diffusion, which I, right or wrong, ascribe to numerical diffusion. It's actually diffusion. Numerical or physical, it doesn't matter, but it is diffusion. So that's the way I became aware and cognizant that this methodology of cascade or linear reservoirs was there. That was 1980. Now, fast forward to the year 2009, and I had always had the impression that the cascade or linear reservoirs could be non-dimensionalized. So I gave a student the job of doing that, and then the story, long made short, is that we put it together in the year 2009. And we wrote the previous paper that I talked about on Monday. And then right after that, immediately I realized that I could go further. Because if you look at this over here, general dimensionless unit hydrograph, May 15th, okay? And here, cascade and convolution, May 25. Those numbers reflect the actual dates when this thing was done. May 15 was what? At the end of the semester. Because we had to assign a grade to the gentleman that was supposed to do this work. And then I sat down, in about a week, we got this thing done, the first paper. Then I realized that I could go further, so I worked another week or another 10 days on it. And by May 25, we had the answer, and we wrote the paper. We had already completed the paper. So I'm going to go over this paper with you today, and we're going to run a bunch of calculators to give you kind of a little bit of practice so that you can do the homework, because I'm going to ask you to do the homework. I thought about this, and there's no reason for you to have to do the hand calculations because the computers are out there. If you ever needed to do this again, the information is everywhere, so you can look at it. And I don't think that's going to happen. Most people in practice now, what they do is they use models that already have these features in it. So you have to know how this works so that you can use the model properly. It would be the wrong thing to do to try to use a hydrologic model without knowing any hydrology. By the way, that's done by a lot of people, but that's not the story that we're about to tell here. So you have to know your hydrology before you can use the hydrologic model, likewise in hydraulics, HRAS, and all the other models too. Okay, so we're going to come in here and say this. The convolution, the cascade linear reservoirs, and convolution, and unit hydrograph convolution, those very respected terms are shown to be one and the same when the cascade parameters are used to calculate the unit hydrograph of the convolution. So there's an if. When the cascade parameters are used to calculate the unit hydrograph of the convolution. In that case, they end up being just one problem, one physical problem stated, and therefore the answer is the same. Now, I should confide to you that at the time I didn't know this, but I realized that was the case once I got the two answers. I looked at them and they were the same. They were not similar. They were the same, which led me to believe that in the back of my mind, I always had thought about this, and we have to go back to Mr. Nash out of Ireland in the year 60, who was talking about these same issues, the fact that there was some coincidences between these two methods that needed to be explored. And I honestly I'll tell you that I don't know if Nash ever pursued this, and Mr. Nash, he precedes me one generation. So if I'm old and almost retired, he must be already in heaven. I'm guessing. I don't want to kill anybody, but I'm guessing that that's the case. He's got to be at least 25 years older than I am. So he would be at this time bordering 100. Okay, so if Nash didn't do it, this remains to be done. And it's an interesting project, by the way, for somebody to prove that, in fact, analytically, because I proved it numerically already. I'm going to prove to you that it is the same in this paper, but it has not been proven analytically. And there's got to be some truth in there in the analytics. I don't think I'm going to get to do that anymore, or not anymore, but yet. So I'm leaving that for somebody else to do, because that's just the way people should work. Remember, Yevevich said that to me one day. He said, Ponce, make sure you never complete a project. I said, why, Professor Yevevich? And he says, because if you finish a project, then you don't leave anything else for anybody to pursue. So you should leave something like 20% there. You know, you could do it, but you don't have to because you know somebody else is going to do it. That's a good advice. And I've tried to do that throughout since I got that advice from my esteemed professor, CIVE at Colorado State. Okay. The convolution is an established method to calculate a composite flood hydrograph, and we quote Sherman. And we also have it in my book. The cascade linear reservoirs is at the core of many hydrologic models, notably the SAR model. The Japanese also use it in a model that they call tank. And I believe around the world in Europe, there may be, I don't know this for a fact, but I know that people use this methodology. It's an established methodology. To be honest with you, at the beginning, when I started doing this in 1979, I didn't think too much about it. I thought it was a numerical gimmick. But I learned since then, it's not a gimmick. It's a very well-founded and it's very powerful, as I will show today, later on. And I'm gonna try to go quick in here because otherwise we'll not finish. Okay, so lesser known is the fact that these two apparently different methods lead to exactly the same composite flood hydrograph, which is what we want to do. All this business, if we could call it a business, is to get to the composite flood hydrograph. In other words, the convolution of a unit impulse, which is the unit hydrograph, and the effective storm hydrograph or effective storm pattern. Okay, so we're gonna substantiate these propositions in here with an example. We're gonna do the two calculations, presumably diverging among themselves, and yet we're gonna get to the same answer. Okay, first of all, we gotta impose or pose an effective storm hydrograph, which is derived from a total storm hydrograph by using a hydrologic abstraction method such as the curve number. At any rate, I have in here an easy way. This is for an example of time 6 hours effective rainfall, meaning we already subtracted the infiltration. Infiltration is not part of this problem. Effective rainfall, as you know, is what runs off only. So we have 1 centimeter in here. In the second hour, 2 centimeters, 4 centimeters, 3 centimeters. It goes up and down like some sort of storm. Okay, it's just numbers that we're going to play around with today. Then we are going to assume a unit hydrograph. No, assume a large basin, because these methods are for large basins. They were purposely tailored for large basins. Why? Because the basins that Don Newton was working with and Sherman were large. Sherman quotes in his paper that he was dealing with basins up to 5,000 square miles. 5,000 square miles is large. It's not the largest I work with. I work with the Pantanal. That's right, the Pantanal of Mato Grosso. That was, I believe it was 70 or 80,000 square miles. Right, correct. But at any rate, I've also worked with the Santa Cruz, which was only 3,000 square miles. But at any rate, Sherman was not working with the rational method. He wanted to stay away from the rational method. He was working with larger basins. 2,000 to 5,000 is what he quotes in his paper. Now, Newton was working also with very large basins in the Columbia. The Columbia is a large basin. It's the second or third. I think it's a third. The third largest basin in the US after Mississippi and Colorado, then Columbia on the Pacific Northwest. So he was dealing with large basins too. So these are for large basins. And so I have in here relative large basin as drainage area 432. You may be surprised, why did I get 432? I actually like the number that Don Newton used in his example of his book. And because we used it so much in our work, we like that number somehow, 432. I'm not sure, I think Don Newton was using square miles, but we switched it to kilometer squares. Okay, the applicable unit hydrograph duration is the same as the storm hydrograph. So the duration has to be the storm hydrograph time interval. So first of all, you got to define the time interval. That's one of the first things that the engineer should do. What time interval am I going to use? Am I going to use 1 hour or 2 hours or 3 hours or 6 hours? Usually that's the case. We wouldn't go less than 1 hour because these are large basins. You know, the larger the basin, the larger the time interval. So let's define at this point that we said delta T was going to be equal to 1, and therefore T sub R has to be the same as delta T. In this case, for our purposes, okay? The T sub R and delta T. The basin is assumed to have relatively steep relief with appropriate cascade parameters. This relief stuff, we're going to be talking about it later because we're going to assemble this whole thing and then apply it to different reliefs. But at this point, we're going to say to get started here, we're going to assume that it is steep relief, and therefore our Courant number is going to be kind of high, and the number of reservoirs is going to be kind of low. So based on experience, we'd say the Courant number is 1, and the number of reservoirs is 2. Suffice it to say at this point that the Courant number cannot exceed 2, so 1 is fine. And the number of reservoirs obviously cannot be less than 1. It cannot be 0. It has to be at least 1. So 1 does not give you any diffusion theoretically. Well, it does actually, because the diffusion also depends on the sea. But 1 is very low diffusion. And in here we're going to look at a good number, so n equal 2. So when we have C equal 1 and n equal 2, we have a program which is called Online General UH Cascade, gives the general dimensionless unit hydrograph shown in table 2. This is the general dimensionless unit hydrograph. That is our hydrograph. That's the one that we derived, okay, in our previous paper. And over here, just to show you this kind of stuff, where Courant number equal 1 and for number of reservoirs equal 2, we did the calculation and we get this result in here, 22237. Let me look at this. 22237 is the same answer. I got smart here. I already know how to run it and I'm running it. Okay, so, but that's not the issue. The issue is how do we construct this? Okay, the applicable reservoir storage constant, K, is delta T over C by definition. And since C is equal to 1 and T sub R is equal to 1, then K is equal to 1 also. Delta T over C. Okay, C is equal to 1, delta T equal to 1, K is equal to 1. And the total time in hours is T star, which is the dimensionless value times the TR. That's the way we constructed the GDUH. And the discharge, this is a discharge that allowed us to construct the DDUH also. Remember that what I said the other day, that if these two numbers are not picked up correctly, 2 and 3, the system's not going to work. You have to pick up the right dimensionalizing parameters or non-dimensionalizing parameters. And we did that because we know how this is done. We've done it many times. So we've been in dark corners many times. So we already know. So now the program Online Dimensionless UH Cascade gives the unit hydrograph shown in table 3. So this unit hydrograph shown in table 3, we would run the Online Dimensionless UH Cascade in here for the basin area. And I believe I don't have it here for some reason. It must be something new. So in order to solve that problem, I am going to do Online Dimensionless Cascade is this one over here. Right. See, I got smart in here. I already have it in hard copy. I don't have to think about this. 432, unit hydrograph duration is 1, storage constant is 1, and number of reservoirs is 2. Right. So now we're going to run it. And we're going to get this number in here. Correct. It is correct. So this is the unit hydrograph by the cascade of linear reservoirs, given the parameters, storage, these parameters over here for the 432. So this is the unit hydrograph of this particular basin of 432 kilometers squares. This is the unit hydrograph, and this is the dimensionless outflow. So the unit hydrograph is 266,444. 266,444, right? So if we come in here, like back in here, 266,444. So that's the right, it's correct. Okay. Then we have the cascade of linear reservoirs. With Courant number equal 1, that is K equal 1, N equal 2, and given the effective storm hydrograph, we use the program Online Routing 8. Online Routing 8, right. Let me pull this out in here so that I will not get confused in here. Right. So Online Routing 8 to calculate the composite flood hydrograph by the cascade of linear reservoirs. Okay, so this is the cascade of linear reservoirs. This over here is not the dimensionless, has nothing to do with the dimensionless. We did this cascade of linear reservoirs much earlier. It's just what's in the book, what's in my book. Because when we did the online calculators back in the middle 2005, 2006, that's when we were really heavily developing the online calculators. And we decided to do the calculator for all the examples in my book. all the chapters, everything was done. So so this is that's why we call it online routing 8, because we did, I think it was 8 or 10 online routings, and this one number 8 in the sequence of the book. So we get this calculation in here, do the online routing, and so this is the example. Online routing OE cascade or linear reservoirs basin routing. So in here we have 432, 432, storage constant, 1. So I'm gonna have you do this in the homework, by the way. And I urge you to be, to have a clear mind, because this stuff could be really confusing. If it's confusing to me, it's confusing to you too, by the way. If I don't look at this for a month or so, it gets confusing. There are too many things happening at the same time. Okay, number of increments is 6 increments over here. I'm hoping that the stuff is over here. And it's not in there. So I don't know what happened. I must have been, oh, I know what happened. I'm not going to share with you that. I'm going to leave it as a mystery. I had to remove, erase the cache. The cache is what has everything in there. And I had to erase the cache because it was required for me to keep going, keep moving. Sometimes they ask, the browsers ask you to remove the cache, otherwise they're stuck on what you did earlier. And it's global, by the way. It's throughout the computer. At least I don't know how to do it single piecewise. So 1, 2, 4, 3, 2, 1. And I know I'm going to run into trouble in the last one. I may not do it because it's going to require for me to sit down and do some typing. And I don't want to do that because that leads to errors, as you know. Okay, so I got the number in here. So now I'm going to run this. I'm running the cascade of linear reservoir straight out of the book. Straight out of the book. And what do we have in here? Exactly correct. 266, 977. Okay, and this number over here, now let's go back over here. I think, no, that's not that. It's this one. So look at this, 266, 977, right? Okay, 266, 977, 222, so it's correct. We got it. That's right, we got it. So we are here, now we're at the cascade of linear reservoirs. We did the cascade of linear reservoirs. And now we're going to do the convolution. So the convolution over here, now we're over here now, online convolution. So we're going to do the convolution. And in here, let me see if I have it. I may not have it. If I don't have it, I'm not going to type it. No, I told you, I erased the cache in the afternoon because the browser wanted me to. So I'm not going to do it, but I'm just going to kind of get over close to it, and then I'm going to have you do it because you're going to have to do it for the homework. So the unit is metric. The rainfall time interval, delta TR, is 1 hour. The number of rain increments of rainfall intensity is 6. Okay, 6. And then the number of rainfall intensity is 1, comma, 2, comma, 4, comma, 3, 2, and 1. So those are the increments of rainfall intensity, effective rainfall intensity. 1, 2, 4. Actually, there should be a word in here, effective, because it's really effective, so not to confuse the people. So I'll do that later. Then the NRCS. Oh, I see. I have to take back what I just said. What happens is this. You put the rainfall intensity, and depending on the curve number you put in here, then you subtract. And this method can do that because we have done this many times. So if I put in here 100, then those numbers 1, 2, 4, 2, 3, 2, 1 become effective because there's no abstraction. And that's what I'm going to do in here. Then I'm going to have a 1 in here, unit hydrograph time interval, and then the number of unit hydrograph ordinates, which came from the second program that we ran. And I am not going to type the 18 values because it would take too long. Besides, you need to type this and think about this through on your own. So here I type the 18 values of the unit hydrograph that I had already calculated in that other program, right? And because I wanted to do it by hand, because otherwise, I mean, you start mixing the softwares, maybe you prove something that it was tricky and you were not intending to prove and so forth. This has to be done independently. Those are two methods that are working independently. They're only connected through the parameters of the cascade. So I put it in there. I'm not going to run it. And then I'm going to show you the, hopefully, here. I'm going to show you the results. This is the results. Now let's take a look at the results in here. The convolution. The first number is 266.667. And over here, the first number is 266.667. The second number is 977.778. The second number is 977. The peak of this whole thing is 3246.091 on time t equal 5. 3246.091. Isn't this marvelous? I mean, I can't find any other word to describe this. These are two entirely somewhat different computations. One of them is convolution, the other one is cascade of linear reservoirs. They operate totally different, they get to the same answer. They must have the same equation, fundamental equation behind it. So that's the end of the story here. To prove that when the convolution is done in the same, using the parameters of the cascade, they exactly give the same answer. So that lends credence to the cascade, because it's basically the same as convolution. You cannot argue otherwise. If people respected the unit hydrograph because of Sherman, they have to respect the cascade because of Don Newton. He was a great guy, by the way. Not given as much credit as Sherman, I don't know why, but he's a great guy. I had the honor of meeting Don Newton in Portland at the end of his career. And I was at the beginning of my career. So that's what I've proven to you that this. Now, the juice of this whole thing is that since we can simulate any amount of diffusion that we wish to pose, we can get the cascade parameters from geomorphology. The cascade parameters are estimated based on the runoff diffusion properties of the basin under consideration. So in other words, a steep basin will get a high C and a low N. A very mild basin will get a low C and a high N. The runoff diffusion properties depend on the terrain's topography and geomorphology. Steep basins have little or no diffusion. Conversely, mild basins have substantial amounts of diffusion. Why do I say that, given the fact that perhaps you guys don't have the proper background? Because of the Hayami formula. The Hayami formula, which we're going to talk about, hopefully, maybe even today. Hopefully we'll get there. If not, we'll touch base on it briefly on Monday, next Monday. Okay, the case of zero diffusion is modeled with C equal 2 and N equal 1. I already proven to you from the previous paper that is correct statement. That is a correct statement. C equal 2 and N equal 1 simulates properly and exactly the response of the rational method. Conversely, the case of large diffusion may be modeled with C equal 0.1 and N equal 10, which would resemble the cases of base flow that Don Newton simulated in the Columbia River in the 40s and 50s. In nature, basins are classified for runoff diffusion on the basis of mean land surface slope. And here I have a preliminary table, which we put together in the year 2009, based on our experience. Very steep, mean land surface slope greater than 10%. The 0.1, I'm sorry, 0.1. Yeah, 10%, I guess. Are there basins out there that have greater than 10%? And the answer is yes. As a matter of fact, my home, I'm sitting here in my home on the, I believe the slope of the street outside of my home is 13%. We've actually measured that. We live up on a hill. Why? Because Professor Ponce doesn't want to get flooded. If I live up in the valley, I will get flooded eventually. Up here, I don't think so. Okay, so mean annual land surface slope greater than 0.1, then you get to from 0.1 to 0.01 to 0.1 and so on and so forth. You can have land surface slopes all the way to less than this. Yes, the Paraguay in the lower basin of the Paraguay has a land surface slope which is less than this number, is 0.501. 501? Yeah, 501. 1 centimeter per kilometer. That's the slope of the upper Paraguay at Puerto Murteño. We have actually measured that back in the year 1979 when we did the work in Brazil. So then the cascade parameters correspondingly, roughly speaking, right, these will be the situations for the cascade parameters. Let me say at this point that when we did this in the year 2009, we had a field of work ahead of us because all this stuff needed to be applied and proven to be correct. Theoretically, we already had proven that it was correct, but in practice, there's other ifs and buts in practice. So we waited for a student to come along and to do this work. Waited and waited and waited. Okay, and we did do it, by the way. That's my next story. So the cascade, these numbers here are thrown in there because based on experience, Professor Ponce's way of expressing his experience. The cascade parameters are going to be roughly these, and the GDUH values, which had already been calculated because we already had the calculators, are these numbers: the peak, the dimensionless peak, and the dimensionless time to peak. And that's it. Those are the numbers. So we get to the conclusions. The conclusions say the method of cascaded linear reservoirs and unit hydrograph convolution are shown to be one and the same, and to give exactly the same results provided the cascade parameters are used to calculate the unit hydrograph of the convolution. In the absence of gauge data, the cascade parameters may be estimated based on geomorphology. Once the parameters are established, the composite flood hydrograph is uniquely determined by either method. Of course, I would prefer the cascade parameters. It's easier, but I shouldn't say that. Well, it's easier from a standpoint of conceptual understanding of it, of the concept of runoff diffusion, but they are the same. One or the other lead to the same answer. We have proven that beyond reasonable doubt. Okay, so now we are going to move on. Over here. No, I'm over here. No, where am I? Cascading convolution. Now I can't find myself. Here we go. Okay, here we go. We're back in here. Are you seeing this now or not? The syllabus?
Yeah, we see the syllabus.
Okay, the syllabus, okay. So now we are in here now. Application, now I'm going to apply application of the general dimensionless unit hydrograph using California watershed data, MS thesis. This was an MS thesis that was done in the year 2017. So we waited from the year 2009 to the year 2017 for a student to come around and want to do a thesis and with me. And I said, well, I mean, we can do this, and a thesis has to be something that is doable. Remember, you don't want to put a student in a position that he or she cannot finish. So he said he had 6 months to do this work. I said, okay, fine. So I said, we're going to gather California data because it's readily available, because now all the data is posted online. All kinds of GIS data available, completely available, free for anybody to use. We're going to use California watershed data, and we're going to apply the GDUH of our creation. And he did that. And he did an excellent job, by the way. The thesis, of course, is about 120 pages long. I am not going to have the time, but I'm just showing it to you as a demonstration, an example of what this gentleman was able to do, taking the theory that we had developed and running with it in practice, okay? He is now working. He has been promoted. He's a young man. He looks younger than what he is. He must be on the order of 30, 32 years old. And he's out there in southern Peru, actually. He's a Peruvian gentleman. In southern Peru, working on some kind of a executive position out there in hydrology, in hydraulics. Okay, so his name is Luis Gustavo Arriza Treyes. Okay, so what did Gustavo is his name, Luis Gustavo. What did he do? He applied our methodology, okay? With all kinds of GIS support, background, the unit hydrograph, we already know that. He picked this out of my book. All these graphs I picked out of my book, just lifted out of my book. I don't care, because he had to do the background, right? All thesis, every thesis has to do a background. So he has the storage, and I'm going over this quick, not intending for you to grasp all of it on the go, because you can't. But if you want to, it's there. You can see it later on. You can go back to refresh your knowledge and go back to my book, because a lot of this stuff is in my book. This stuff is all in my book. I mean, as a matter of fact, these figures are from my book. Linear reservoir routing coefficient, that's in my book also. Okay, likewise, everything else. The instantaneous unit hydrograph. Here, I'm going to stop in here to tell a story. The famous or infamous instantaneous unit hydrograph. originally due to Nash, by the way. But then it was later pursued by a lot of people, and they gave it a name. They call it a geomorphic instantaneous unit hydrograph. Among them, my colleague, Rodriguez Iturbe, who was originally from Venezuela, but he's in the US now. He's a professorship somewhere in the East Coast. Oh, I think he's in Texas right now. Rodriguez Iturbe, he's about my contemporary, maybe a couple years older or younger for that matter. He and other people pioneered in this GUIH for geomorphic instantaneous unit hydrograph. I honestly, with you, I never really understood the background on this stuff. But I told Luis Gustavo that he should review everything because otherwise people are going to say, why didn't you do this? So he reviewed everything and he put all the stuff that Rodriguez and I put in here. And Rodriguez and they did a lot of empiricism, like the fourth category method. Remember, I told you this: deterministic, probabilistic, conceptual, and parametric or empirical. And you can tell that these formulas are empirical. 218 and 219 are formulas from Rodriguez's work. Oh, and they have all kinds of numbers that pull out of the air here. 131, 444. I don't like that. We don't have that sort of stuff in our stuff. Our stuff is all very clean, conceptual, not empirical. Okay, the concept, I'm going to take that back because at the end, we're going to get to a little bit of empiricism, but that's almost at the end, like 5%, not 100%. The concept of runoff diffusion, we had to put in there, Professor Ponce, I claimed the origination of the phrase runoff diffusion. I already told you that. Runoff diffusion is in reservoirs, runoff diffusion is stream channels. We've already seen that. This is my famous S-curve that I developed in 1977. Then the equation of convection diffusion of Hayami, right? Hayami, 1951, developed this equation without the V squared, just with the Q naught over T. And then we added the V squared later. Actually, it was Dug in 73 and in 82 that added another component. And of course, in true research, good researcher fashion, they never completed the work. And then I came in 1991 and completed the work and expressed the whole thing in terms of the Vedernikov number. Uncovered the Vedernikov number, not discovered it. Uncovered from oblivion, I guess you could say. And the Vedernikov number is defined as 223. And the Vedernikov number is used to define the occurrence of roll waves. And these are the roll waves which occur in steep line canals. And then we have runoff diffusion in catchments. We already covered this ground with you guys in this figure, which you already know. Remember, I said, and I think one of the homework said, show me that the kinematic wave does not diffuse. And the answer is, well, the hydrograph has a sharp peak, which already shows that it does not diffuse. All the other hydrographs have smooth peaks, right? So that is the concept of runoff diffusion. The general dimensionless unit hydrograph, there it is. There's our creation right here, the GDUH. And basic classification, which is coming out of our previous paper. Methodology, I'm going to speed up in here. Methodology overview. The methodology of this thesis, by the way. The methodology is simple storms, assemble the rainfall runoff. For each event, calculate the unit hydrograph, calculate the cascade parameters, convolution and inverse convolution. Oh, inverse convolution. What is inverse convolution? Well, we know what convolution is. In convolution, you have a rainfall and you have a histogram, and you get the runoff. In inverse convolution is you got the runoff and you're going back to find in convolution, you go from the unit hydrograph and the effective storm hydrograph to the flood hydrograph. In other words, the green is convolution. From here with this to here. And in inverse convolution, we go from here with this to here. And it is an extremely complex process, which I placed in my book. And the reason why I did it is because I figured out that we had to write the book in a friendly way if we wanted to sell it. And we did sell it. But don't make it too friendly, because then you won't sell it. Okay, so I decided to put a couple things. There's a couple of areas in my book that are tough. but there's a couple out of 200 or 100, let's say 100. 2% of my book is basically unreadable. We put it in there purposely, okay? To, I guess you could say, why not say, gain a little respect by everybody else, all right? So this inverse convolution, it's a tough problem, but it can be done. It can be done. There it is. This is the inverse convolution technique. Oh, there it is, the inverse convolution. We got to use this little formula in here. 3. I don't expect you to spend a lot of time on it because you will if you wanted to do this. This is very complicated. There it is. There's the calculation of the inverse convolution, which I believe I had in my book, how to do this. This is tough. The chances for you to do an inverse convolution are extremely nil. And I should tell you a story. When I did the Muskingum Conch back in the late 70s and early 80s, and the Muskingum Conches was a direct calculation. But then the issue is, there was a gentleman over at GS that wanted to do an inverse routing. And he basically hired me. He said, Ponce, I need to do an inverse routing. Can you do it? I said, sure. All we do is just revert the whole thing, reverse it. Start at the end and go back to the beginning. And we did it. We did a small project. It was a small project, a few $1,000 to write to him, to write a report to him so that he could mimic what we had done and do in reverse routing, which is used. So this is kind of the same, on the same vein of reverse convolution. Yeah, I think so. Having said that, that's both are inverse or reverse calculations. So general dimensionless unit hydrograph, we already covered this ground. And these calculators and these graphs, we already covered that. It's in my calculators. The colors are in my calculators. Okay, so for C equal 2, we have these and we plot these. We used Excel to plot that. These are for C equal 2. This is for C1.5, for C1, for C.5. You would recall that this is similar to the paper that we just read last Monday, but these are in color, not black and white, in color. And it also applied for not only for the C's, but also for the N's. Can you see the N's in there? For each curve, there's in 1 to 10. And lo and behold, they do give the higher the N and the lower the C, the more diffusion. There it is. That's the maximum of our calculation, because we can do further, more. I can show you a calculation with Z.01 and N equal 25, where the response is, it looks like a horizontal line next to the axis. In other words, totally, completely diffused. It will take forever to the hydrograph to be reflected. That's the thing about these calculations. And this is the opposite of the graph. For the various C's, the C is a curve parameter as opposed to the N. We needed to do this to show everybody the capabilities of this number generation tool. It's a hydrograph generation tool, all kinds of hydrographs. Okay, it really is fascinating. I'm going to make a comment here that Sherman never intended to do this, and yet his calculation reflects what we have done by the other method. It's really amazing. Okay, so we have in here, these are results for our calculators, results that you are going to get very familiar with because you got to do your homework. Then the data analysis. Okay, and I'm going to finish it here in 10 minutes. The data analysis, maximum elevation. This is a lot of work, by the way. Luis, however, was very adept with working the computer. And what facilitated his work and his finish on the right time, and like I say, under budget, on time and under budget, was that I provided to him all the calculators that he had to use. He hadn't to do, let me say this, he didn't have to mess with any programming. It's himself. There's no Excel. The only Excel that he did was to plot, not to calculate. Because to this day, we don't have a plotter. We could, but we haven't gotten into it. I was going to do it, but we never did it. I dropped the ball at that time. I mean, a plotter with our online calculators. But, you know, there's ways to skin the cat, as they say. We can take the results of our calculators, the table, and plug it directly into an Excel sheet and plot it. And everybody knows how to do that. There's people very adept at putting together graphs out of Excel sheets. And since those graphs come from somewhere else, there is no question as to their accuracy. All Excel is doing is plotting. The problem with Excel, if they get into calculations, there's a high risk that it could go wrong. because you got to control so many cells, right? Let me not get in there. Okay, so this innovation, Campo Creek. So we chose 10, he chose 10. I advised him what to choose. Campo Creek, we had done a lot of work in Campo Creek from 2006, 2007, 2010, actually earlier than that, early 2000, 2001. So we were very familiar with Campo Creek. Downstream view of Campo Creek near its headquarters. This is the central view of Campo Creek in Campo Valley. This is the famous NOAA NWS rain gauge at Campo, California. Of course, you guys don't know the history of this rain gauge. In 1891, I think it was February, I have the data somewhere. There was a storm in here where it rained 11 inches in 100 minutes. I was going to say 100 inches in 11 minutes. No, 11 inches in 100 minutes. And that's considered to this day to be, if not the probable maximum precipitation in the entire state of California, among the very close to the probable maximum precipitation. Let me repeat, 11 inches in 100 minutes. So an hour and a little more than an hour and a half, it rained 11 inches in this place in Campo, which, by the way, it is a dry area. Campo Creek, it rains only 500 inches, 500 centimeters per year, not inches. That's a lot, 500 inches, a whole lot. 500 centimeters per year. 500 centimeters? No, it's 500 millimeters, I think. At this point, I'm getting confused. I handled so many numbers today. At any rate, the point is that this is a famous rain gauge because it took all that rain that in the 1891. Of course, I cannot tell you it was the same gauge. What I can tell you is that it was the same place. Because I happen to know the guys that handle this rain gauge. There are kind of, not colleagues, but acquaintances over the years that I worked in Campo Creek. I don't remember the names right now, but Johnson is there, the family. It's a homestead family that they've owned the property for more than 100 years. They measure the precipitation at this gauge every day, if it rains, of course. Okay, so the Campo Creek subbasin, Campo Creek, like I said, we're very familiar with Campo Creek. We've gone all over the place out there. So I'm going to finish in here by saying that we did the methodology as best as we could, and it worked beautifully. We have not only Campo Creek, we also have Mojave River near Victorville. We have, and look at the maps and so forth. Luis was very good with GIS. What can I say? Mojave River near Victorville, the hydrographs, major hydrographs. Amargosa River at near Tecopa, California. They're all California rivers. Petaluma near Petaluma, and so on and so forth. Russian River near Guerneville. Russian River is north, about 100 miles north of San Francisco. Los Gatos Creek near Coalinga. This is in the Central Valley. Central Valley. That's a picture of the Central Valley, by the way, that I believe I took. And so on and so forth. The next one is Cottonwood Creek. That's at the end of Cottonwood Creek is at the end of the Central Valley near Cottonwood in California. And northern end of the Central Valley. Salinas River, we know where Salinas River is near San Francisco. We had to look for rivers that had good data, by the way, and that's easy to find. Well, it takes a lot of time, but it's not difficult. The Shasta River in Montague, California, the Shasta River, the drainage and so forth, the GDUH model application over here, examples, Campo Creek. Look at this, average measured and predicted. I mean, you can't tell me that we didn't do it right. It's perfect. You typically, hydrographs give you 20–30% error, and that's acceptable. Here, the error is about 1%. Here, I don't see the difference. This is number 3, the same. Of course, these are calibrated, by the way, meaning meaning the blue is correct. And the other one is calibrated, meaning we have to vary the C and the N in order to get the right numbers, right? It's a fitting. It's a fitting. We didn't just guess the red. The red was fitted to the data, which is the way it's supposed to be. Likewise, they're all very good fits. They're all very good fits. This one's perfect. So that's the end of the story. Very good ending, very good story. He finished, the gentleman finished the thesis, and then he did some calculations over here, which I'm not going to get involved in this because it's too much at this point. I just wanted to show you that this stuff works, and it has already worked. And then he created this diffusion number, which is the division between the number of reservoirs and the Current number, and then diffusion number versus drainage area. These are just plots, empiricism at the end of a conceptual model, which is good. You should do a conceptual model and then come up with some empiricism, not the opposite. The opposite is no good. Don't start with empiricism because you'll never end. Okay, so that is the end of, and he even has an example application here, which I'm not going to get through because it's too much information. Okay, so the predicted DUH for the sample application, unit hydrograph, and summary and conclusions, success, total success, okay, of our methodology, applied our methodology to 10 rivers in California. So with that then, now we're going to move on to the next paper over here, a hydrodynamic watershed model. This is a video actually. I'm gonna do not the raster but the video, kind of to change the mode of presentation a little bit. Let me say this as we start this subject, that we had done lumped models. So far, lumped models. I briefly talked about distributed models in our first section of our class when I presented the model by Rosa Aguilar. Remember the thesis by Rosa Aguilar that was done with us in the year 2014. I told Rosa, I said, I have a Fortran program of the diffusion wave model of catchment dynamics. Your job is to convert it to PHP and do all the components that are missing and finalize it and present it. And she did that. It took her a year to do that work, but she did it. In the process of doing that, she learned how to use online calculations and so forth. So, so that's one story. The other story is, who else has done distributed modeling and when? Oh, that's the answer of this video here. The two-dimensional hydrodynamic watershed model. Now, let me say at this point, if you guys are confused, that Rosa did a one-dimensional model. She did the Wooding plane, which is a one-dimensional model, which the water flows into the plane and then it flows into the channel and then it flows out of the outlet. That's one-dimensional model. This thesis was a two-dimensional model. So the history is why and how and by whom, and that's the subject of this video.
I met Professor Ari Ben-Zvi of Ben-Gurion University of the Negev in Israel, in New Delhi, India, in December of 1993, while I was attending the International Conference on Hydrology and Water Resources convened to honor Dr. Satish Chandra on occasion of his retirement as director of the National Institute of Hydrology, India. I recognized Ben-Zvi by his name tag, and being somewhat familiar with his early work, I engaged him in conversation.
In other words, I met Ben-Zvi over at a conference, and I already knew who Ben-Zvi was because I had read his work, namely the work that we're going to be talking about here today. So I said, oh, yeah, right, sure, you're Professor Ben-Zvi, I know you. So we became friends. That is the card to get anywhere, okay? So we became friends, colleagues with Ben-Zvi back in 1993 because he was not extraneous for me. I already knew who Ben-Zvi was. Ben-Zvi is not a very common name.
Ben-Zvi had a pleasant demeanor. He confirmed that in the late 1960s, he had completed a PhD at the University of Illinois under the supervision of Professor Ven T. Chow. His thesis dealt with the application of the dynamic wave to overland flow in a two-dimensional context.
That's it. That is a mouthful. This story has a lot to do with my entire career, so that's why I am enjoying this right now. The application of a two-dimensional model for overland flow. So what happened was this: Venti Chao, Vence signed up with Venti Chao because Venti Chao was a well-known guy at the time. He had already written a book. He was in the process of writing, he had already written 2 books. So Venti Chao must have told Vence V, you're going to do this. You're going to do the two-dimensional model, distributed two-dimensional model. And this is going to be for the first time because you're getting a PhD and it has to be for the first time. So these people were doing this for the first time. My guess would be 1968. It is 1 or 2 years before 1970.
He confided to me that he had not used the model since the time of his graduation.
So he never used the model. He developed the model, he graduated, went back to Israel, but he never used the model. That's the issue here. He never used the model. Why? Because it was too complex a model. It is too complex a model. And suffice it to say at this point that we now know that it was too complex a model. But Venti Chao didn't know that. And Vence V was not in a position to argue with with Venti Chao. So he did it. He did the work and completed the model. He graduated and he left. Okay. And I say that with knowledge because I happen to know the experience of Professor Woolheiser, who at about the same time, roughly about a few years earlier, actually it was at about the same time, 65 to 67. These guys were working 68 to 69 to 70. So it was about the same time. It is probably that they didn't know what they were doing. I mean, one didn't know what the other one was doing. But what happened was that Liggett, Professor Liggett, my esteemed colleague Liggett, who was over at Cornell, big time university, had Woolheiser as a student. And he told Woolheiser, he said, we are going to do the dynamic wave model. But they were doing 1D in the open book. You see the difference? They were doing the same equations, but Liggett and Woolheiser were going to do the 1D, and Vence V and Venti Chao were going to do the 2D. They were in Illinois, etc. Actually, Illinois and Cornell are about the same level, so I can't say they were better. They were just doing something different, okay? But within a couple of years or even earlier, Woolheiser went over to Liggett and said, you know, Professor Liggett, I can't do this. I'm not going to graduate. It's too difficult. So then they decided in common accord, as they say, to not to be too ambitious, and they reduced the scope of the wave to the kinematic wave. They actually developed the idea that the kinematic wave was going to suffice. So Liggett and Woolheiser then went on to develop the theory and practice of the kinematic wave 1D. While a couple of years later, Venti Chao and Vence V were doing the dynamic wave in 2D. So my contention is that if Liggett and Woolheiser couldn't do the dynamic wave in 1D, Venti Chao and Vence V were not going to be able to do it either. And that is in fact the truth. They didn't do it. They did it. They graduated, but he never used it because it became too complex, too difficult to use. I could talk here for 10 hours on this subject, but I'm not going to. Obviously, we don't have the stuff, but I know what I'm talking about. That's exactly what happened.
That the dynamic wave does not apply to overland flow because the prevailing slope is usually large enough to make the flow either kinematic or diffuse.
Look at this slope in here. The overland slope, this slope in here is 20-30%. This is in Peru, by the way, in the Andes of Peru. It would apply if you had a slope of 0.001, but not 0.1.
For the dynamic wave to be applicable, the prevailing slope would have to be very small, say on the order of 0.0001, which is typically not the case. Many similar experiences confirm this conclusion. For instance, David Woolheiser mentions that in the 1960s, he and James Liggett set out to prove the utility of the dynamic wave in overland flow computations, and after much study, ended up changing their minds.
That is Liggett talking to the journal, publishing in the Journal of Hydraulics Journal. He says, we couldn't do it. My professor, David Wilheiser, by the way, at Colorado State, middle 70s.
Instead, they focused on the applicability of the kinematic wave, which led to the development of the kinematic flow number.
Where is it? That's it, I found it. Okay, so let me clear this up in here since we already finished. That's a good story, by the way. The fact that Wilheiser and Liggett couldn't do it, Chow and Vensvi did it, but to no avail. They never used it. I have remained friends with Vensvi over the years, you know. And back in the year 2014, he called me up because he was going to do the homage, I guess the celebration of Chow's life, professional life. And he came up with the idea of putting 3 or 4 sessions, I think it was 3 sessions together. So he called upon 12 people around the world to celebrate the life of Chow. And he called me up and said, Ponce, you could do it. I'm going to invite you to do one of the 12. And then he said, choose a topic. I said, well, I'll give you an answer in 2 or 3 weeks, 3 days. So I thought about it. I said, I could talk about my S-curve, which, by the way, it's a great job, but I mean, it's a great piece of work, but not too many people have actually dug into it. And then I also said I could talk about Chow, fruit, and Vedernikov. And he really liked the idea of talking about fruit, shoot, how am I talking here? Chow, fruit, and Vedernikov. So I ended up writing that paper for him. And because it was central to the thing, because I was going to be talking about Chow, comparing it with fruit and with Vedernikov, right? And it merits and it's appropriate that that comparison should be done, and it wasn't done. It had not been done at that time, 2014. Why? Because Vedernikov was hidden. Nobody could talk about Vedernikov. Who is Vedernikov? Nobody knows, right? So therefore, I did that in 2014, and that has given me a lot of accolades in terms of bringing up the subject of Vedernikov to the surface and so forth. And I, of course, thank Ari Vensvi for inviting me to participate in that celebration of Chow's 2014. It was at the 50th anniversary of the publication of his original Handbook of Applied Hydrology, which was a very good book of the time. Penti Chow wrote 3 books. And then, of course, he's now deceased. He was professor for 30 years. He was professor over at the University of Illinois at Urbana. Okay, so then the last thing we're going to do here is a paper that this is my most recent paper. I wrote this paper with A.C. Scott, and it's dated July, August, September, October. So it's 4 months old. Comparison between kinematic and dynamic hydraulic diffusivities using script online over land. And the subject of this thing was that Andrea Scott had specialized in hydraulics, and she took all my classes, and she wanted to do a special study. I believe this was a special study, so that she could graduate. You know, in our program, our graduate program, everybody has to do a thesis or a special study. I'm not going to get into details because you already know that. If you don't know, then you should find out. But the thesis is worth 6 to 9 units, while the special study is only 3 units because it's like a mini thesis. Okay, so this is considered to be a mini thesis that Andrea C. Scott wrote at the time. And the issue is this: we have the kinematic and dynamic hydraulic diffusivities, and the kinematic hydraulic diffusivity is that of Hayami, and the dynamic hydraulic diffusivity is variously that of Doug or Professor Ponce, because I worked on this also. So the question is, theoretically and presumably, the dynamic hydraulic diffusivity should supersede and should be better than the kinematic one. That's the accepted knowledge, I guess you could say. So therefore, how good is it? How bad is the kinematic hydraulic diffusivity as compared to the dynamic hydraulic diffusivity? So we set out to do that. So the first thing we need to look in here is, what is the hydraulic diffusivity? The hydraulic diffusivity, the first gentleman that wrote about the hydraulic diffusivity is Hayami, 1951, in a famous paper, of which I published the first page of the paper, because I didn't want to publish the entire paper. It's about a 40-page paper. Nobody's going to read it, but I wanted to show the origination of this concept of diffusion. Okay? It's here, is the underlining in there. It is an equation of diffusion containing a term of advection. So I did not invent the word diffusion. Diffusion has been around. Diffusion is one of the most prevalent processes in nature. Without diffusion, the world as we know it will be unlivable. And because of diffusion, we're able to live here, okay? Because otherwise it will be chaos. Lack of diffusion would mean chaos. And since we have a normal, more or less normal life here on this earth, there's a lot of manifestations of the concept of diffusion, which is a second order process, by the way. Convection is a first order process, convection or advection. He writes advection by, I wrote in the con. So that's the origination of the concept of diffusion. Hayami, 1951. Dewey in 1973 was invited to give a series of lectures here in the US by the ARS, the Agricultural Research Service. Agricultural Research Service is the research branch of the Department of Agriculture here in the US. They have a whole lot of, it is kind of a think tank. So they decided to invite Duke, who was a very well-known gentleman at the time in Ireland, professor over at, I believe, University College in Dublin. And they invited him, and he came over and wrote a book. Before he came, he put everything that he knew into the book. He called it Linear Theory of Hydrologic Systems. Duke's Linear Theory of Hydrologic Systems. The lecture 9 is Mathematical Simulation of Surface Flow, which I read several times when I was a student, by the way. I would take this stuff out there and read it, because I figured out that I really need to know this stuff. So this is Duke. 1973, wrote a book on the stuff that we're looking at. And in that book, in that chapter, he mentioned this equation, which, as you can see, it's a variation, an improvement on Hayami's. Hayami didn't have this parenthesis in here, which Duke had. And Duke is correct, by the way, because he used a lot of theory and so forth. We cannot argue. Duke is correct. Subsequently, there were a couple of gentlemen from Poland that decided to go to work with Duke. And Duke must have said, I wasn't there, but Duke must have said, you guys, you know, this equation 2 is good, but it could be improved. I think it could be improved. Researchers very often have a hunch. I have a hunch that this thing is not enough. So these two gentlemen worked a number of years. I can't recall, but it must have been several. Working out of Ireland or perhaps out of Poland. I don't know where they were located. But they, in 1982, published this paper, Duke et al., which, this paper, by the way, hydrodynamic derivation of storage parameters of the Muskingum model. Okay, so I read this paper very carefully. And by the way, this is an extremely difficult paper to read. I gave it to Nicole Nocitelli, 2013. She was doing a special studies with me, which I believe we have touched upon or else. And she gave up. She couldn't do it. She's one of the smartest persons that I have seen in math. She couldn't do it, and I couldn't do it either. So we gave up. We kind of fiddled with it. We put a little bit into our papers, but this stuff in here is very difficult. I don't recommend that you guys spend any time on this stuff. But they did get to a final product, which is this is their final product of all their mathematical exercise. They said that the 4 was not really a 4. It was 1/4 squared in the beta, and they brought in the beta in there. What is the beta? The beta is the exponent of the rating. So all that mathematics was necessary for them to change the 4 into what it really was. This was the beta, because the beta was 3/2. The beta standard, let's put it, the central number was 3/2. So 3/2 minus 1 is 1/2. 1/2 to the square is 1/4. So that's the 4. So that it's already said that was correct. So do it all were also correct. Then that was 1982. We toyed around with these formulations, these papers through the 70s, 80s, and finally it dawned on me one day, as Marcus said, in the kitchen table. It must have been in the kitchen table. If it was not in the shower, because it does happen to that, by the way. You're thinking about it and it all of a sudden pops up, the idea pops up. It popped up, my idea popped up that this number here was indeed the Vedernikov number. Beta minus 1 squared F squared was the Vedernikov number. So we put it in there in 1991. We wrote this paper called the kinematic wave controversy. That's the original version, the kinematic wave controversy. I'm sorry, that is not it. It's the other paper, this one. New perspective on the Vedernikov number. What happened was that in 1991, we were privy to this equation. And we that year published 2 papers. So I've shown here the 2 papers where we mentioned this issue of the Vedernikov number. It's over here. Right here. This is the first time anybody came up with this equation. And we mentioned the originators, took it all, Ponce 1991, my other paper. So basically we came out and published this equation over here. And then from there, we got dedicated to working on the Vedernikov number. Long story, by the way. And I don't believe we have the time to do now credit or justice to this issue. So we're going to leave it for later. So we have I'm going to finish it here in 1 minute. So we have the overland flow model, the test problem. We've done this work for 30 years. What actually happened was that we could not find hardly any difference between one and the other. Much to our chagrin. I mean, I thought that there was going to be a 1%. But no, there's not even a 1%. Probably the answer is 0.1% or 0.2%. Too small to worry about it. So all our work of 30 years have gone down the drain. Why? No, the answer is more subtle. Of why is it that these hydrographs don't show any difference? Look at this. If you find any difference in there, let me know, because I can't find it. And we looked at the data that was coming out of the computer. It's very small difference. We looked at it. We toyed with it. The only thing that we could come up with is that we were simulating kinematic waves. And when you simulate kinematic waves, you're not going to be able to show diffusion. And if you don't show diffusion, then you're not showing the Vedernikov affecting the diffusion. And that's exactly what we said in here. I'm going to finish in here in 1 minute. Effective channel slope. So this is an interesting story of research. Okay. Okay, here. The results show that the 2 formulations, the difference is negligible. The reason for this behavior strikes at the core of shallow wave propagation mechanics. Kinematic waves do not diffuse. Therefore, for kinematic waves, any difference in the way diffusion is calculated would be negligible. Conversely, for diffusion waves, any difference in the way diffusion is calculated would be small. So the question is, this wave that we're trying, what is it, kinematic or diffusion? The wave tested in the reference test problem, which is a standard wave, by the way, is a typical wave found in hydrologic practice. So it is very likely to be kinematic. To prove this assertion, we use the kinematic wave, and we get the number 4320 greater than 171. So this wave that we're trying over there is extremely kinematic, 10 times more kinematic than what it could be. So we now have the answer to the puzzle. If we want to try the difference between 2 diffusive formulations, we should use a diffusion wave, not a kinematic wave. But to use a diffusion wave would round against the actual practice, because most waves are kinematic. And that is the reason why Liggett and Woolheiser decided to drop the dynamic wave and not only go back to kinematic, but also make possible to Woolheiser to graduate with a PhD, because he wasn't going to do it with a dynamic wave. Very long story that could occupy me for several hours, but I'm not going to do it because we already ran out of time. So as you can see, these things remain in the realm of real fascination. There's a lot of things out here that could be pursued. So anyway, so I'm gonna stop in there, and we have completed what we were supposed to do. So next week we're gonna get into a different subject. It's gonna be channel routing. Thank you very much.